Okay, good afternoon, everybody. My name's Rob Ramsey, and I'm a group leader and co-chair of the GI Cancer Program. Peter Mack, a member of the VCCC Alliance. It gives me great pleasure to chair this session today. As an aside, I'm also a patient with a particular interest in today's topic, so I'm looking towards a very interesting afternoon for us. So before I go any further, it's important that I acknowledge the traditional custodians of the lands upon which myself and today's presenters and audience are located. I'd like to pay my respects to elders past and present and extend that respect to other Indigenous Australians present online. So before we kick off any further, we need a few housekeeping things to keep this seminar moving along, this webinar. So I'd just like to note that today's webinar is being recorded. So if you missed anything, you want to go back and check, it'll be available on the VCCC Alliance Open Learning page, which is a great resource for you. If you have any questions for today's presenter, you can add these via the Zoom Q&A function. And please submit your questions throughout the presentation as you think of them, so we can run through them at the end of the session. So it gives me great pleasure today. I've just been talking to Dr. Ruwan Tennakoon as we're getting ready for today's presentation. He's got a really interesting research background. He comes to us from the RMIT University. He's a lecturer in artificial intelligence and in the computing technology area of RMIT. His main research interests are in computer vision, machine learning, and medical image analysis. He's published over 30 peer-reviewed papers in journals that I'm not familiar with, lots of really interesting acronyms. But I think the really cool thing that I'd always like to acknowledge is he has 3 patents, which is quite an achievement. He's led and contributed to several projects in the areas of quantitative image analysis, computer-aided diagnosis, and industry partners have been working with him, including the Ford Motor Company, IBM Research, St. Vincent's Hospital, and the Erasmus Medical Center in the Netherlands. Dr. Tennakoon holds a Bachelor of Science with honours in electrical and electronic engineering and a PhD in computer vision. He's completed his postdoctoral training at RMIT in the School of Engineering and IBM Research. He is currently a member of the RMIT AI Innovation Lab and Intelligent Automation Research Group. I really am excited to hear what you're going to tell us today. I've read your paper most recently on this topic, and I'd like to hand over to you. So thank you very much for joining us today.
Thank you, Rob. Let me share the screen. Good afternoon, everyone, and thanks, Rob, for the introduction, and also thank you for inviting me to give this presentation. Today, I'm going to talk about our recent project on developing an AI-based tool for incidental detection of prostate cancer. Before we get into the prostate cancer project, let me go through some of our prior projects in medical image analysis to give a brief overview of what we have been doing in the area of medical image analysis. So I've been in this area for about 10 years now, and I initially started by looking at and designing tools to analyze low-dose CT images of the lung. One of the earliest projects that I was involved in is to do with developing a robust tool to compare CTs taken before and after a particular treatment. Especially the aim here was to identify the changes in a particular tumor due to the treatment process. And in doing so, we need to distinguish these differences between the physical changes in the patient's body as well as the motions that the lung undergoes. So that's one of the projects. And another project is on developing motion segmentation or understanding motion on 4D CT images. And 4D CTs are basically a sequence of 3D CT images taken across a breathing cycle. And you can think of this as a video of 3D CT images. And here again, we were interested in identifying the motion patterns of different tissue in and around the lung in order to identify whether they provide us significant information to diagnose different types of diseases. We have also worked on data from different screening programs. One special project was the one that we did with a hospital in Netherlands, which uses the data from the Danish lung screening trial. Here, our aim was to identify and quantify emphysema in low-dose CT images. In doing these type of projects, we have gained a lot of experience in terms of applying AI or computer vision techniques to medical imaging tasks. And medical imaging tasks generally comes with their own sets of challenges, unlike the natural image processing tasks. These include things like the limited data availability and also the challenge in acquiring annotations that are required to train these deep learning models or machine learning models. Now, apart from the CTs or lung CT images, we have also worked on many other different types of imaging modalities. One such example is the work that we did on optical coherence tomography images. And these images are of the human retina. And what we are interested in this project, that particular project, was to quantify and identify fluid buildups underneath the retina so that we can identify different types of diseases. So I hope that this brief overview gives you some idea about the types of projects that we are interested in at our lab, and also the skill set we possess in terms of analyzing medical images. Now let's dive into the topic for today. Today, I'm going to talk about our recent work done in collaboration with St. Vincent's Hospital in Melbourne on developing an incidental detection tool for prostate cancer with computer tomography scans. Again, this is a collaboration between RMIT and St. Vincent's, and the medical expertise for this project came from St. Vincent's, and the project team there was led by Dr. Mark Page and Peter Brochi. And in terms of the AI expertise, it's provided by our AI discipline at RMIT University. And I should acknowledge the PhD student who put a lot of effort in making this tool a reality, Stephen. And without him, this project wouldn't have been a success. All right, so let's get into understanding why we need an incidental detection tool and how this tool operates. First, in order to understand this, let's see why incidental detection is important for prostate cancer. Well, we all know that significant portion of our elderly population, elderly male population, is affected by prostate cancer. And in fact, this is the second most frequent type of cancer found in men after lung cancer. It's also known that if detected at an early stage, the survival rate of prostate cancer is quite high because of the slow progression of the disease. Unfortunately, though, prostate cancer does not generally present symptoms until it becomes locally advanced. And therefore, it's difficult to rely on the appearance of symptoms to do early detection. And we need other mechanisms such as screening programs or incidental detection tools in order to detect prostate cancer early and to manage it effectively. Now, for many different other types of cancers like breast cancer and bowel cancer, there are well-formulated screening programs in Australia. Unfortunately, there is no screening program for prostate cancer in Australia. So in order to understand why this is the case, let's look at how prostate cancer is diagnosed. Usually, prostate cancer is diagnosed using a blood test called the PSA test or a digital rectal exam. And this is confirmed via and ultrasound guided biopsy. Now this PSA test, which is a blood test, looks like a good candidate for a population-based screening program because a blood test is quite accessible, as well as there's almost no side effects in such a test. Unfortunately, though, the performance of this test itself is quite contentious, and many countries, including Australia, have decided not to run a screening program based on this blood test. So if you look at the position statement on prostate cancer screening by the Department of Health in Australia, you'll find that they mention that the current evidence indicate that the PSA test is not suitable for population screening as the harms outweigh the benefits. All right, so this means that the incidental detection tools or mechanisms are really important in managing prostate cancer. Well, how about other imaging modalities? Are other imaging modalities used in detecting prostate cancer? Well, in terms of prostate cancer, the most prominent imaging modality is the multiparametric MRI. There is a standardized protocol for reading MRIs for prostate cancer called the PIRADS protocol. And this protocol actually standardizes all stages of prostate cancer detection, acquisition, interpretation, and reporting. And I've also seen that there are some recent work on using MRIs, mainly MRIs without contrast for screening of prostate cancer. However, these are very recent studies and they are not generally adapted yet. And also Australia hasn't looked into or adapted these screening programs yet. All right. So what about CTs? Can they use for incidental detection of prostate cancer? Well, CTs make a lot of sense in terms of incidental detection of prostate cancer because CTs are widely available than MRIs for as a start, and also many individuals that are in the high-risk category for prostate cancer undergo CT imaging for other reasons. All right. So if we have a tool that can identify prostate cancer on a CT, that means that we can cover a large cohort of the population, and this allows to be effective at detecting prostate cancer incidentally. One negative thing about CTs is that we all know that there is a high radiation dose associated with the CT. Therefore, this type of modality is not ideal for a screening program because we don't want to put anyone, a patient that's healthy, through a CT scan. However, here we are interested in using CTs for incidental detection. That means the patient is going to get a CT for some other reasons, and the risk or the radiation risk is already justified because of the other reason. And the prostate cancer detection here is almost a bonus for us. All right. However, there is a significant problem. The main problem with CTs in using CTs for prostate cancer identification is that CTs does not have good soft tissue contrast. So what this means is that CTs are not suitable for humans to diagnose prostate cancer. Well, this might suggest that our initial hypothesis that we can somehow use CTs together with AI in order to detect prostate cancer in feasible, right? Luckily, though, there are some recent studies that suggest otherwise. I have mentioned here a couple of these studies, and these studies have shown that there is some correlation between the findings of prostate cancer on MRI and contrast-enhanced CT images. While these studies give us some assurance that our hypothesis might be valid, these studies are rather limited in several aspects. Mainly, these studies are done on very small cohorts of patients. And also some of these studies have concentrated only on certain regions on the prostate and have not looked into the entire prostate region. All right, so however, for us, this is not such a big issue. We know that further investigations are required in order to determine the diagnostic capability of CT in prostate cancer. However, we are not after developing a new diagnostic tool. What we want to do is to build a system that can do incidental detection. And such a system would have a organization similar to this one. So a patient would come in to get a CT because of a broken hip or abdominal pain or some other reason. The patient gets scanned and the radiologist would analyze that CT for that particular cause. Now, if we have an incidental detection system, an AI system, we can also feed that image to our AI system. And this system will provide the radiologist with additional information. And now the radiologist can take appropriate action based on this new information he or she sees. Right? So this is what we wanted to build. We wanted to build this system that can collaborate with the radiologist and enhance its options in terms of identifying prostate cancer, the CTs. And in order to build such a system, we need to first answer this question, which is, can clinically significant prostate cancer be detected on CTs using AI? So to the best of our knowledge, there was no other studies done in terms of using CTs with AI to identify prostate cancer. While there has been several studies that I talked about before, that these studies concentrated on using CTs and read by humans in order to identify prostate cancer. All right. So in order to answer this question, what we first did was we collected the retrospective data set from the St. Vincent's Hospital. Our data set consists of 571 patients. Out of this, 139 patients were PCA positive. So these were patients who are diagnosed with clinically significant prostate cancer. And these diagnoses were confirmed using biopsies. The remaining 432 patients, which we call controls or negative patients, these patients were males older than 50 years of age who have undergone CT imaging at St. Vincent's Hospital for some other reasons. And we have made sure that these patients have no prior history or a suspicion of prostate cancer, hence they are called the control patients. So our approach now is to develop an AI-based system in order to separate between the scans of these two different groups. We need a predictive model that can, given a CT scan, that can say that this is from a prostate cancer patient or this is from a control patient. And so, all right. So let's have a look at our approach. So our approach is based on this deep convolutional neural networks, which are very popular these days. So these deep convolutional neural networks, or deep learning in general, these techniques are very broadly applicable to many tasks these days for image classification, things like understanding voice, understanding text, and so on. And if you have used Google or any social media platform today, you must have used used the services of a deep neural network in doing so. Right. So our system is also based on these deep neural networks, and these deep neural networks can learn a predictive model by looking at the examples that we provide. And the examples that we provide are going to be coming from the data set that we have collected from St. Vincent. So in that data set, we have the CT image and also the correct label, which says whether that scan is from a prostate cancer patient or not. All right. So let's look at the pipeline that we use to accomplish this task. So in our pipeline, we take a CT image first. and then we crop the prostate region from the CT image. So this cropping is done mainly because we wanted to concentrate our model to look into only that region and not be confused by the regions around it, so that we need this prostate cropping section, right? So once the prostate is cropped, we feed that into a second module which do some image enhancements. This will sort of help the neural network to learn the model easily. All right. Once we do this enhancement, that enhanced prostate region image is fed into a convolutional neural network, and for this we use a special type of convolutional neural network called a 3D convolutional neural network. And now this network can predict whether that scan has prostate cancer or not, and it will spit out a probability based on its decision. All right. So now we can see that by showing the examples in our data set, we can train this model to become good at this task. However, there is a problem, and this problem is usually we know that these deep learning models, or CNNs, they require a large amount of data to learn a robust model. However, we don't have that much data. We only have few hundred images in our data set compared to few thousand of data that is typically used to train this type of model. So we have to come up with mechanisms to help the learning process of this neural network model. And there are many techniques that we can use to make the learning process easier for the neural networks. These techniques include data augmentation, things like transfer learning, as well as self-supervised learning. And in this project, we use this technique called self-supervised learning to help our network learn a robust model. Let's have a look at how we employ self-supervised learning in this context. So what we do here is that we take a CT scan from our data set, and what we do is we add some corruptions to that image. So what we do in terms of corruption is something called patch swapping. So we take a patch from some area in the image and we swap it with another area in the image. So what this does is it actually adds some noise, and now what we want our network or the model to do is we want it to reconstruct the original image from the corrupted image, right? And the hope here is that if the network can actually reconstruct the correct image from the corrupted image, it will identify, it will understand some semantic information about the CT scan itself. And this is quite similar to the fill in the blank type questions we typically get in an English exam. So in fill in the blank examples, the examiner will take a sentence in, let's say, English, remove some words and ask the student to complete the sentence. And the student, in order to complete this sentence, has to be aware of the context of the sentence, as well as he needs to know the grammar, right? And the idea is quite similar here. If we corrupt the image and ask it to reconstruct, we'll know that the model has to learn something about how the data appears in a normal format, right? So far, when we do this self-supervised learning stage, it will understand how the normal images look like, or natural CT images looks like. However, it does not know still to distinguish between prostate cancer and no prostate cancer. In order to do that, we need a second stage where we use that smaller label data set in order to do something called fine-tuning. What we do here is we now put that data set with the correct label of whether there is prostate cancer or not. And the network will now learn that additional thing that is required to differentiate between prostate cancer and no prostate cancer. All right, so this is the approach that we took in order to develop our deep neural network model or deep CNN model. Next thing is that we wanted to evaluate the performance of this model. All right. In terms of evaluating the performance, we use five-fold cross-validation. And performance measure, we primarily used area under the ROC curve. So, or in other words, it's called AUC. And AUC produces a number between 0 and 1. 1 meaning that it's a really good model that correlates well with the labels we have in our data set. 0 means the labels are negatively correlated, and 0.5 sort of indicates that this is not a good model that is doing some random sort of classification, right? So usually the AUC value is going to be between 1 and 0.5. Now, when we evaluated our model, we can see that vanilla 3D CNN with trained without any additional help would get about 82% or 0.82 AUC. While this is a reasonable value, we can see that when we help the network with this self-supervised learning techniques and data augmentation techniques, we can get a much improved performance. We were able to get around 87% AUC for this particular data set, right, on this task. Now, the next question is, how does this value compare with other systems, and can we use this system now for incidental detection of prostate cancer? Well, in order to find that out, what we did first was we extracted a subset of our original data set, and then we asked 2 radiologists at St. Vincent's to read these images in that subset for prostate cancer, right? So the radiologists are experienced radiologists, but they were not given the diagnostic information about. They had to look at the scans themselves and come up with whether this scan has a prostate cancer or not. So here we have plotted the performance of those 2 radiologists against our model. The performance of our model is shown here in this orange ROC curve, and any point above, any technique that is above the ROC curve means that that technique has better performance than our model, and any point below says that that particular technique has lower performance compared to our model, and so on, right? You can see that when compared with the radiologist performance, our model has achieved significantly improved performance. And this is in line with the literature and the prior experience as well. We know that radiologists or humans find it difficult to distinguish between prostate cancer or non-prostate cancer in a CT scan. Now, our model, however, has been able to do this task well, and this may be because the AI system is capable of picking up subtle variations in the image that are not visible to the naked eye. All right. So this gives us a sort of very good indication that our model is doing well. However, we wanted to go one step further, and we wanted to know and compare our system against the state-of-the-art techniques, which is mainly based on MRI. So what we did was we compared our system with 2 MRI-based systems. The first one is the PIRATES-based system. This is mainly humans reading MRIs using the PIRATES protocol. And the second one is a neural network or an AI system reading MRI scans. Now, the performance of these 2 are plotted here, and we can see that they are almost on top of the performance or the ROC curve of our model, indicating that they have comparable performance to our system. All right. However, there is some thing that needs to be noted here. The MRI-based system and the CT-based system are not evaluated on the same patient cohort. Therefore, we can't really do direct comparisons. And here we are not claiming that we can use our system as good as MRI-based systems. What we are trying to say here is that the performance it gets on the CT data set is comparable or somewhat similar to a MRI-based system. Therefore, this system it can be used for detection purposes. All right. So far what we have done is that we have developed this prototype software, and the results have shown us that we can do incidental detection, or CTs have this information that is required to differentiate between prostate cancer versus non-prostate cancer. And this is the work that we recently published in scientific report earlier this year. All right, so the next question is, what's next? What's our next step? Actually, what we wanted to do is we wanted to build this software system that can be deployed in practice across different hospitals, including St. Vincent's Hospital. And in order to get to that goal, we have to take several steps yet. All right. So the first thing that we are interested in doing is to do a clinical validation of this technique via a prospective study. And this study would give us more indications about the benefit of using such a system. And we can now think about directly comparing our system with other MRI-based systems and so on. Right? And also this will give us an opportunity to work with other stakeholders, that covers things from a patient's perspective as well. And we have to think about how we need to present this information if this system is deployed in a hospital and so on. Apart from that, from a technical point of view, there is a couple of questions that we need to answer before taking this and deploying in a hospital as well. The first one is that we need to verify that our model is capable of adapting to different settings. And also we need to make sure that our models are transparent and interpretable so that we can present the information in a useful way to the radiologist, and this system becomes more user-friendly. All right, so let's have a look at these two steps in a bit more detail. First, let's look at the generalizability or adaptability of the model to different settings. And what do I mean by different settings in this scenario? Well, different settings can be caused because of different types of equipment. Maybe the data set that we acquired is from a GE CT scanner, and we wanted to know and make sure that this model will work in other types of settings as well, things like Siemens or Canon or other equipment that is coming from different vendors and so on. Another type of differences might be due to the hospital. So we are not necessarily looking to develop a tool that can only be used in St. Vincent's Hospital. We want to make sure that this can be utilized across different hospitals as well. However, when you talk about different clinics and hospitals, there can be subtle variations in the acquisition parameters and things like that. And we need to make sure that our models would work across these things as well. For the humans, this is not a big issue. So in order to highlight this, I've shown here a simple example. So these are three different OCT scans coming from three different patients. And these scans are captured using three different machines, a Spectralis machine, Cyrus machine, and a Topcon machine. And when you look at these images, you can see some subtle variations in the noise pattern and the sharpness of the images themselves. However, if a human is trained on one type of image, he wouldn't find it challenging to adapt to the other types of images. Unfortunately, though, the AI systems find it challenging to adapt across. So we know this by experience. These models that is developed on data captured from one device might not generalize well to other devices. Actually, we need to give it some help in this direction, right? In this case, this is mainly because these machine learning models or deep learning models have a large amount of parameters, and some of these parameters use and learn some useful correlations in the data, and some of these might learn spurious correlations that are not useful. When we go from one domain to the other domain, the useful information or useful correlations are still valid. However, these spurious correlations that are learned on noise patterns and things become not valid, and therefore we can we can face issues in this regard. Right. So in this direction, we have already started doing some work. What we did was the St. Vincent's dataset actually is acquired using two different types of machines, a GE machine and a Siemens machine. And what we looked into is whether a model that was developed purely on the GE-based data can be generalized to Siemens data and so on. And the results so far shows that our model would generalize across these different machines. We also are planning to go one step further, and we are going to test our model on data that is captured at different hospitals or different clinics. And for this end, we have already collected a data set that is from another institute, and we are in the process of verifying our models across these data as well. All right, so the next item we were interested in was the model interpretation. And as I explained earlier, what we really need is to facilitate the decision making right? So at the moment, the model that we have developed is sort of like a black box. Given an image, it will say whether that image or CT scan contains prostate cancer or not, and it will give some confidence level to that. However, it does not reveal the rationale behind that decision, and this type of black box models can create friction when we try to adapt it to practice. And this is mainly because if in our case, if the AI system and the human agrees on a particular CT scan, there's no problem. The human will use the AI output to validate his opinion, and that's a good thing. However, the problem is when the two things does not agree, right? In that case, our model does not provide additional information at the moment, and this can be an issue. And in order to solve this, we can think about building in explanation capability into our model, and this is something that we have started looking into as well. And the explanations can be in terms of the location information. So the model now can tell, I think that this scan is of a prostate cancer patient, and the reason I think is because of this region. And now the radiologist can go back and look at that region in the original image more closely and either change his opinion or not change his opinion based on the new observations that he did. All right, so this is one thing that we can build into the model. We have already done this in other the projects that we have done. For example, in the work we did with the Danish lung screening trial data, we provided explanations that look like this. Here what we are saying is that we say that a given CT scan is of a patient with emphysema, and we also give this color coded location information indicating where emphysema is on a particular CT scan. We do this via color coding, and now if a radiologist missed any part, he can go back and make sure that he agrees with the outcome of the AI model or not. All right. While this type of explanations are straightforward for emphysema type classification, there is subtle challenges when we try to apply this type of things to prostate cancer, mainly because for emphysema, it's easier. We know that for humans, they can diagnose emphysema by looking at CT scans. However, when it comes to prostate cancer, we discussed earlier that humans find it challenging to identify prostate cancer. Therefore, even if we point out the location in which the model thinks that there is prostate cancer, it might still not be very useful for the radiologist or the human, and therefore we need to think about presenting this information in a much better way. And this is something that we are currently working on. We are looking into whether we can enhance the original CT image in a way that we present the information better to the radiologist, and therefore increase collaboration between the AI system and the model. All right. So that brings to the end of my talk. And in summary, what we have developed is we have developed a neural network-based pipeline that takes in a contrast-enhanced CT and can predict whether a scan has prostate cancer or not. And the initial results that we have observed shows that CTs contain enough information to do this task, which is to separate the PCA scans from the non-PCA scans. And this provides a strong promise for real-world application of this tool for incidental detection. Now, there is some work left to actually to come to a stage where we can deploy this model in a real setting in a hospital. And we are currently looking for funding avenues to get this work completed. And a side note is that this project might also indicate that we can develop similar type of tools for other types of cancer for incidental detection using AI as well. And we have already started several projects with St. Vincent's in this direction as well. All right. Thank you very much. And I'm happy to answer any questions you might have.
Thank you very much, Ruwan. I found that really very interesting. And it's from a number of points of view. Obviously, I mentioned about my own experience, but the interface between medicine and engineering is really important. I think it's underplayed and not well understood. So it's been lovely to see how you've been able to work with the team at St. Vincent's. So there's a few questions in the chat. I will present those to you, but I've got a few of my own as well. So the first question is really, it's a bit of a public health issue question, and I might be able to help you if you don't want to answer it yourself. But the question is about, you talked about the harms of doing PSA screening on a population basis. And I wonder if you'd like to share with us why there's a concern about using it as a test, particularly standalone.
Well, I don't think I am the best person to answer this question, Rob, because I lack the medical expertise in that domain.
Well, maybe I can help a little bit. I too don't have medical qualifications, but I do understand that there's a concern about the worried well, that is increasing the anxiety amongst men who have got a PSA reading that is out of context and may not have been managed with the right kind of counselling and support. So that's one of the issues about PSA. I suppose it's always a matter about the relationship with your GP. That to me that's a key interface. So another question that actually came to me as well, and I thought it was a really good one. you're talking about incidental CT results. Have you discussed with your colleagues, I'm not sure this is done at St. V's, but it certainly is done at a number of places, including at Peter Mac in this precinct, that's PSMA, PET scanning as a complement to what you're doing, or perhaps even the application of AI on PET scanning, because that's something that gives you an activity signal rather than a structural signal, which is really what the CT is doing.
Yes, that's a great question. So we initially looked into using CTs with PET imaging. So when we tried to develop these techniques, one challenge we had was at St. Vincent's. What they do is, when they do a CT, they also PET scan. They also acquire a CT, and this CT is not contrast enhanced. And our initial sort of work in this direction showed that the non-contrast enhanced CTs does not have that capability, or that does not have that information to distinguish between prostate cancer and not. Right now, we have another data set from a clinic in New Zealand, and in that clinic, they provided us with the PET information as well as contrast enhanced CTs. And this is exactly what we are looking at. And we might be able to also improve the explanation capability, because PETs give us a much more localized information prostate cancer.
The other important thing about PSMA PET is that if the cancer happens to have gone somewhere else, that could be important, but it's not usually used in an incidental sense. It's very targeted for men who've got a potential of having prostate cancer. So to explore a bit more deeply in terms of the imaging, we have another question about the use of contrast dyes. You use intense image intensification and lots of computer manipulation, but what about the use of dyes? Is there a place for that?
Yes. So at the moment, as I mentioned earlier, we first started with low dose CTs, and we found that those images are not so suitable to be used for this type of application. Then we moved into the contrast enhanced ones, and that's where we found that we can actually do this using an AI-based system. So maybe there is future opportunities in developing better contrast agents as well. But in summary, the system we have developed at the moment requires a contrast enhanced CT.
Yep. I think that there's a lot of opportunities to develop this further. Once you've got a pipeline of AI embedded in your own research, but probably more importantly, getting confidence from the radiologists that they're prepared to have the conversation with you. That's going to
exactly. This is something that I really enjoyed about this project. Actually, the problem itself is not something that sort of we envisaged. The problem came from radiologists at St. Vincent themselves. So they are the ones who formulated the problem, and got us involved in developing this system. So they are really positive, and it's great to work with such a team that understand the capabilities of AI.
I think if it's done with respect and diplomacy, you can do an awful lot with your colleagues across a whole range of specialties and skills. So I've got another question here about the use of neural networking and how it might play a role in identifying men at risk of high risk of prostate cancer or locally advanced cancer. So let's just sort of expand the argument away from the encapsulated tumor localized with the prostate. The next challenge might be, do you pick things up with an abdominal CT scan that goes outside the confines of the prostate? Is there a thought about where you're going with that?
Yes. So, of course, we have these sort of areas that we'd like to explore a bit more. So, this is what at the moment, this is not the end product that we want to get into. We actually want to explore those type of other things as well. We've started looking into a couple of other types of cancers as well on those CTs as well. You know, there's so much potential in this work, and maybe it's not only our group, there might be others interested in this as well. And this might lead to, you know, people using this type of incidental detection techniques for a range of other types of diseases as well.
Right, I just want to add a little comment. One of our listeners added in an important point about the role of measuring total PSA versus the commonly used test. I'd also add that the trajectory of increase of PSA is also part of that reckoning. A comment coming from a patient might emphasize, and not one who's medically trained to give any advice, but I would give the point very clearly that anybody or any man in this situation who's worried, the relationship with your GP is really, really important. So I've got one question, very technical one, but I'm wondering if it influences the comparison when you're looking at comparing to the radiologist and the scoring with your technology. You work with a cropped image to provide the programming that you need to analyze. Were the radiologists given a similarly cropped image, or did they get the full pelvic image and then they had to work out to look at the prostate, or were they already guided towards the prostate to call that? How did that go?
Yes, so we actually designed a special interface, and we only showed the prostate region to the radiologist as well. So we didn't give them the surrounding information. So
the detection of incidental cancers is something that I've observed in my observations at in MDMs, and that comes up quite commonly with the PET scans, as it turns out. Incidental lesions elsewhere from what the dedication of the MDM might be. So I think this is starting to become more of a problem. But if you do a total body CT scan, knowing where to apply the deeper analysis is going to be something that will require an algorithm about where that might go. Yeah. So I don't know how we're going for time. I think we're doing pretty well here. I'm looking for any more questions. I think I've caught most of them. I apologize to our audience if I've inadvertently not recognized someone's question. I think I've covered that reasonably well. So I think we might have come to a comfortable and natural end here. I'd really like to thank you, Ruwan, for coming along and sharing with us what you're doing. I think you're going to have a bigger and more important place in this space. The Alliance is a perfect environment to get cooperation across different centres. And of course, the more that occurs, the more real world the application of AI is going to be in medical imaging. So I just remind the audience that they can go and see the webinar as a recording, and it's available on the Open Learning page. So it leaves for me to once again thank you very much for a really interesting seminar, and I appreciate your efforts in this space. And in this virtual world, AI is becoming more and more important, and I'm sure your contributions will only grow. So thank you very much, and to our audience.